Hello and welcome to today's webinar. Our topic today will be stress-strain analysis. My name is Jasmin Hartung and I work at Dlubal Software in the Department of Marketing and Public Relations. Today I will present this webinar together with Lukas Sünel and Frank Faustich, who can now briefly introduce themselves.
Yes, hello also from my side. My name is Lukas. I'm hired here as product and customer support engineer, usually with the focus on the interfaces, but I'm also doing webinars and support for stress-strain analysis and steel design. I will present this webinar today.
Hello, my name is Frank Faustich. I'm responsible for product engineering and quality management, and today I will try to answer your questions.
Okay, great. Thank you very much. We can now turn off the webcam so the viewers can see the whole screen. Okay, and before we start with the presentation, I'd just like to mention that you are able to ask questions during it. Therefore, you can use the control panel that you can see on the right side of your screen. As you can see here, this is the point where you can put in your questions. We will try to answer all of them during this webinar. If there are too many questions and we can't answer them right now, we will send you your answer via email. And if you just like to watch the webinar for now and pay attention and have questions afterwards, you can always send them to info@dlubal.com. Okay, now I'll hand over the screen and we can start with the presentation.
All right, I think you should see my screen now.
Yes, we can see it.
Yes, thank you. Yeah, then let's start. Before we go into the live demonstration, I would like to quickly mention the contents of today's webinar. In general, I want to give you an overview of the stress-strain analysis add-on. I will start with the probably most used functionality, the calculation of stresses of members, surfaces, and solids. In the next chapter, I basically continue with the stress analysis, but for our newly implemented line welded joints. Newly implemented means we have them since we have RFEM 6. In the last chapter, I intend to show the strain calculation, of course, in combination with the plastic material behavior. I will do it as a live demonstration, so I didn't prepare any additional PowerPoint slides, so I will jump directly into the program. And today I also would like to work with predefined files in order to keep the focus on the essential topics. What do I have here? I have a mixed structure here, mixed by the meaning of I have here a member structure, surface elements, and also solids. Let me quickly change the rendering so you can easily see the differences. On the bottom, we have this member structure. Then I converted a certain part of my members into a surface structure, as you can see here. It's just the continuation of my members if I display them again. And on top of that, I have my solid model on which I will place some loads. Regarding the modeling, which is maybe also interesting to know, we have here this, so in general, we can model members, surfaces, and solids in one structure, which is already quite nice. And if you think about the load transfer and this correct transfer of the stiffness, you have to take care of some things when you have a 1D element and 2D elements. By simply converting these members into surfaces, as I did it here, often you don't have a proper or a not correct defined connection. You can see it on the left. The surfaces in that area are now basically supported on only one FE node. Yeah, the FE node where this member, where this member connects to the web of this beam. That is of course not correct. You would definitely get singularities in that area, and the stiffness transfer is also not correct. Another example can be found in the center. We have here a pipe section. And when you convert a pipe section into a surface, you get, of course, the pipe surface. And in such a case, you have no connection at all. Yeah, you can imagine the member is in the center of that circle, and the surface is of course not connected to that member at all. So here we also have to do some modifications in the modeling to have it properly connected. And I have it here, I just didn't show it so far. So I will cancel my visibility mode, and the connection can be done in, let's say, two ways. I can use so-called rigid surfaces, and this simply will transfer all my forces and my deformations that I have in this beam, or also vice versa in that surfaces, via a stiff surface onto the other side. In the center, it's even more crucial, because with this stiff surface or rigid surface, I'm connecting my member with my surface. Yeah? Before I had no connection at all. And again, of course, all deformations and internal forces will be transferred from the beam to the surfaces equally, let's say. An alternative modeling can be, or is visible here on the right-hand side. Instead of using a rigid surface, I simply assigned rigid members onto the boundary lines of my surface model. Yeah? A member with a member type rigid, and it works similar to my rigid surface. Yeah. So this is how you can connect a 1D element with a 2D element. The rigid surface or rigid member may help you here. Regarding the connection of a surface model with a solid, well, this is quite easy. The surfaces are defined by the boundary lines. Yeah, these are those lines here, which you can see. And these lines are placed inside the boundary surface of that solid. And we have a so-called automatic object detection in those surfaces. So the surface detects that there are lines placed inside the surface. And if that's the case, then the FE mesh generator will automatically consider those lines when the mesh will be generated. So we have a fixed connection between those lines or these surfaces and the solid. Yeah, so far regarding the modeling. Regarding the loading, this is German names, never mind. I have two load cases. I have my dead load case here, and then some load in my live load case. Yeah, that's all I want here in that example. And of course, we have the combination of those load cases using a ultimate limit state design situation and a serviceability limit state design situation. Now, if we want to design such a structure, we have to deal with, we have, let's say, two main designs that we have to run. We have to run a stress analysis or a cross-section check for our objects, and we have to run a stability design. Regarding the stability design, I would like to take a look at the results first. So that's what I will do now. I will calculate the, let's say, the important load combination. I have just one here that actually matters. Yeah, the combination of the dead load and the live load. And let's have a look at the results. Maybe just on the members for now. I can display the axial forces in here, maybe in a different view like that. All right. And what I can see here is I have, of course, compression in my, let's say, columns or in my members. Yeah. So compression is, of course, a sign for buckling. Yeah. So if I have compression in members, I have to check buckling. And what else do I have? I have some shear forces inside, but they are really small. So shear buckling is most likely not an issue. I have really small torsional moments. I can neglect them. And my bending moments, My and Mz, are also quite small compared to my cross section or to the dimensions of these beams. So I would say also the bending moments can be neglected. What does it mean? If I neglect the bending moments, then lateral torsional buckling is most likely not an issue. And if I check again my structure, I have all these diagonals here that are connecting to my columns. a pipe section, which is where lateral torsional buckling is not important at all. So I think it's fair to say lateral torsional buckling is not an issue here. What could be an issue is, of course, buckling. But for buckling, I can use some limit checks or some let's say some specific checks to judge if buckling is actually an issue. And such a check can be found inside the Eurocode 3 in chapter 6312 in brackets 4. The formula basically is you take the axial force in a member and you divide it by the critical force of a member. And if that is smaller than 0.04, then you don't have to run a buckling or buckling check for a member. If we switch it around, if we say the critical load of a member or the critical force of a member divided by the existing force, if that is bigger than 25, then buckling is not an issue. And this is a value we can check via a specific add-on. And I want to do it quickly before I start the stress strain analysis. So if I go into my add-ons, I can activate the structure stability add-on. Now this will calculate this critical load factor, which is the same as I just said, the NCR, the critical force divided by the actual force. And I will calculate it in my in this specific load combination. I can activate now the calculation of the critical load, and I will start the calculation. So this add-on will calculate this critical load factor. It will also calculate buckling lengths and so on, buckling length factors. For me, important is now only the critical load factor. And again, if that is bigger than 25, then buckling is not an issue. Just a few seconds more. All right, there we are. So how can I display these results? Well, I can switch in my tables to this stability analysis add-on. And the first value that will be shown here is already the one that I'm interested in. The critical load factor is 29, which is bigger than 25, so I'm good. And if I want to analyze it even further, I would have to check, I would have to look for an eigenmode that actually deals with the buckling. And this could be, for example, the force eigenvalue, eigenmode. And here we see this would be some kind of buckling for my columns. I have here the factor 34.5, so much bigger than 25. So I can easily say buckling is not an issue. Now I excluded buckling and lateral torsional buckling. That means it is enough to simply run a stress analysis for the structure. I can do it, let's say, in two ways. First of all, I would like to check what result RFEM, the basic RFEM, gives me. Yeah? So I go back into my static analysis results without using any add-on. Yeah? And I can see that RFEM calculates the deformations, of course. It calculates the internal forces in members. It calculates the internal forces in surfaces and so on. But it also gives me the stresses in members. So for example, the equivalent stress according to Mises. It also gives me the stress inside surfaces. And of course, also in my solids. So this is now I'm displaying the stress on all elements. And you could use the information in this panel on the right-hand side, or this max-min information on the bottom left of this graphic window to see that the maximum stress for members, for surfaces, and for solids is below the yield stress from my steel S235, 235 Newton per square millimeter. We are below, actually below the limit. So the stress check is fine. Now, if you prefer a design ratio, yeah, not just a graphic which shows that stresses are smaller than 235, if you prefer some kind of a design ratio, then you could use the stress strain analysis add-on for that. So let's check this out as well. I will activate the add-on in my add-ons tab, as I did it before with the structure stability. The stress strain analysis add-on can be found on the right-hand side under the design add-ons. And usually we have to deal with the standards. Yeah, if we run a steel design or a concrete design, then the standard is important. The stress strain analysis add-on is standard independent, so we don't care in that case. Now, when you activate an add-on, you get a new entry in the tables, and this is how I personally usually deal with the add-ons. I go into my table on the bottom and click through these subtables. Let's do it for this example. Just use a different display. I'm here in the input data in the first subtable design situations, and here I can decide which design situation should be analyzed. Of course, it makes only sense to analyze the ultimate limit state and not the serviceability limit state design situation, so I deactivate the second one. In the next table, you can select which objects you want to analyze. Here, all objects are selected. Of course, you could select the surfaces or the members that you want to analyze if it's not all of them. In my case, I will simply analyze all. There's another table which looks quite similar, but this is called objects to analyze stress ranges. So if you want to run a fatigue design afterwards, or that's what you have to do. And for this design, you need the stress range. Yeah, so the difference between the maximum and the minimum stress on a certain location. Then you can also select those objects where you need the stress range for. So in my case, let's say I need the stress range in my solids, then I'm selecting the solids. The additional tables are, let's say, more or less for an overview. Yeah, you can see which materials and which sections will be analyzed here. And the section and the thickness table have one additional functionality that I would like to mention briefly. You have the possibility here to run an optimization for sections or for thicknesses. What does it mean? Well, when you have a structure like that, you define the section. You define the material in the section. It's an assumption usually. You don't know if the what do we have here? HEA 200 is enough. Is it too big? Is it too small? And when you run the stress strain analysis, you get a design ratio, maybe 20%. Then you would go back if you want to be, let's say, economical. Yeah. Then you go back and you exchange it for an HEA 160, and then you do the same again, and maybe 1 or 2 times more until you find, let's say, the best solution. And this iterative process can be done automatically. Yeah, you can select here in this column, use other section for analysis, the option optimize current row. Current row means the row, the whole range of HEA sections. Yeah, so the add-on will look in the row of the HEA sections, which section is the best, and that means for which is the design check still fulfilled, but the smallest one of them, yeah, or the one with the least weight. We have the same optimization for surfaces. So let's say you have a specific surface and you're not sure which thickness is appropriate. You can, wrong click. You can activate here also the optimize functionality. Then you get an additional window, and here you can define the minimum thickness, maximum thickness, and the step. And then it will look for the best thickness. I will not use this now, just as an information. Now we have 3 additional subtables here, configurations. In those configurations, you can define which stress do you want to analyze. Yeah. You could, of course, select all of them. But usually that's not what you care of. Usually you care only of, let's say, maybe the equivalent stress according to Mises, maybe the total shear stress, maybe the total normal stress. This is maybe what you're interested in. So with the click in this table, you select which stresses you want to calculate, and with the center column, you can also define the limit stress. You can see here the limit normal stress, limit shear stress, and limit equivalent stress is selected. So we try to do it automatically for certain materials. For some materials we can't. In that case, you can select here user-defined, and then you can enter a value in the last column. In my case, I'm using the limit normal stress. All right. For the surfaces, the same configuration basically. Let's select only those two. And also for the solids, we have a configuration. Again, I'm only interested here in the equivalent stress according to Mises. And just to show it, we can enter here a manual value, maybe 235 Newton per square millimeter for my material, which is an S235. So that makes sense. All right. In the last tables, you can assign the different configurations that you may have to your members, but you can also do it graphically. So let's say you have multiple configurations for your members. You can edit the members and simply assign the configuration in that window to them. So the handling, I'd say, is quite easy. We already finished with the input, so we can run the analysis. All right. So after the analysis, we get results graphically and also in the tables. Let's start with the tables first. If there are design checks which are not fulfilled, or you have selected maybe objects that can't be designed, then you get an overview table. If everything is okay, you won't see this overview table. Just in case something is not correct or you get a warning, then it will show up as it is shown here. We can see here for some members and some stiffnesses or some surfaces, basically, the design is not possible. That's nothing which should bother us. At the beginning, we said, please design this or analyze all members. All members also included the rigid members. That makes no sense, basically. We have no section for them. We have no material assigned to them. We can't analyze them in this add-on. That's what this add-on just tells us here. They are not designable. And the same, of course, for the rigid surfaces. So nothing we have to worry about in that case. If you want to see the details of the results, then you can go into the stresses on members tables or stresses on surfaces and stresses on solids, of course. So this is the stress or the table output, of course, with different filters by design situation, or maybe for each surface, the maximum stress, or for the various thicknesses that we have assigned here. So these are the filters basically for the results. We can also display these results graphically. On the left, you can see that maybe we have here, and let's say updated result navigator now for the stress strain analysis results. And here we can select the stresses in our members, on the surfaces and so on. I think this is quite clear how to handle that. And the last information here, we also selected the solids for a stress range analysis. Again, those results can be found in the tables. This table looks a bit different, as you can see. You can see, let's say, the minimum stress, the maximum stress, the range, the difference basically. And you can also see from which combination or which combinations are linked to this stress range. All right, again, we could display this graphically. So far regarding this basic functionality, the stress analysis on members, surfaces, and solids. And now I would like to switch to my second chapter, where I would like to show you the stress analysis of a line welded joint. For that, I have a different structure. And let me quickly explain it. It's a 2D truss member. Basically, the tension forces will be taken over by these round bars, the compression by these HEA sections. And one particular detail joint I wanted to analyze with surfaces, basically. You can see the rest of the structure is again a beam structure, a 1D element structure, and this specific detail I want to analyze in detail using surfaces. I modeled the connection plates here, these tension members are connected to this bolt, and this bolt transfers then the forces onto my connection plate. The force transfer, for those who haven't seen that before, can be done like this. Usually you create an opening inside that surface, of course, where the bolt goes through, yeah. But if you have a bolt in the center as a member element, it's not connected to the surface. So somehow you have to establish this connection between, let's say, this node and this connection plate. And this can be done using a specific surface. So I filled that surface again with that hole with the surface, and that surface has a stiffness type without membrane tension. And this specific type simply acts only under compression. So you can imagine if we have tension forces in that tension member, then the bolt will be moving to the, let's say, top left now, yeah, upwards, and we will get compression in that area. We will get tension on the back side of this plate, but since this this surface will fail under tension, we have only forces on the left-hand side. And this is, let's say, a good feature to consider this, this connection between the bolt and the hole. All right. So far regarding the modeling, I have, of course, my steel connection plate here, and the steel connection plate should be welded to my top flange of this eye section. Now, if I want to design such a weld, I can use this new object which we have in RFEM 6. It's called line welded joints. You can find it under types for lines. And you can define a new type in here. Let's say this weld that I want to design is a T-joint, a single fillet weld, continuous arrangement, and the weld size is 4 millimeters. So far, so good. And now I can assign this type to my lines, and the weld should be placed here, of course. And it's not enough to just connect the line. We also have to select the line. We also have to select the surfaces that are participating, basically, and that's this connection, or the steel connection plate, and the upper flange of my beam. Okay, that's how we can define such a line welded joint. We will show it as such a dotted line, yeah, on each of the participating surface. And if you want to design such a weld, you need the stress strain analysis add-on. Basic RFEM 6 won't give you any results for that line welded joint. So it's required to have the stress strain analysis add-on. And that's why I'm activating it again. Now let's go quickly through the input of this add-in. I'm starting again with the design situations. Yeah, I think that is clear. Objects to analyze. In that case, I don't care about the stresses in my members. I don't care about, or let's say I want to select just some of the surfaces that I want to analyze, not all of them. And of course, I want to analyze my line welded joint. Stress ranges, I don't care in that case here. And I will continue with the surface configuration. Again, I will select just some of the stresses. I'm not interested in all of them. Maximum shear stress, maximum stress according to Mises is quite interesting for me. And now we have also a new configuration for my line welded joint. Yeah, so each specific object has its own configuration: surfaces, members, solids, line welded joints. And in here, yeah, it looks basically the same. I can select which stresses I want to calculate. Even though you select maybe all of them, not all of them will be shown. It depends. For my fillet weld, which I have here, I have two different methods, the simplified method and the directional method, for example. Let's say we are using the simplified method. That method, or for that method, I only need following stresses, those four, and the resulting weld stress. If I select the others as well, they won't show up in my result table. They are not part of this simplified design method. So that's why I select just those four, those five. And same logic as before. When we select the stress, it means we tell, or we say to the add-on, please calculate the stress for this specific stress type. Defaultly, or as a default, we do not get the limit stresses for the welds. You can see it here, it's selected none. Why is that the case? Well, we are standard independent in that add-on. That means, or standard independent. The limit stress for welds is, however, standard dependent usually. Yeah. So according to the Eurocode, you have a specific formula. According to the, I don't know, American standard, it's probably a different one. So as we don't select a code at the beginning, we don't know what the limit stress will be, but you can enter it yourself, of course. Let's say we assume here a Eurocode design, then the limit stress for this simplified method would be for an S235 FU divided by square root 3 multiplied by beta W multiplied by gamma M2, which is 208 Newton per square millimeter. I could also enter this limit stress for the other types, but it doesn't matter. I only need it for the resulting stress. All right. So far, so good. I defined all necessary inputs, and now I can run my stress strain analysis again. Okay, I get the overview table. It deals, well, it shows me some exceeding stress for my surfaces. I will take care of that later on. Now I'm interested in the line welded stresses, and we can see here, okay, we have an existing stress of 71 Newton per square millimeter, which is smaller as the limit. So we get the design ratio, and yeah, the weld has been checked. Yeah, we can also display the results graphically as usually. Yeah, just let me show it quickly. We get the diagrams also shown here. Maybe it's better to select a specific visibility for them. The different stresses, normal stress, shear stress, also resulting stress, and of course also a stress ratio, and that's it. You can of course print these graphics into your protocol as you are used to in Dlubal. The tables will end up in the protocol, so I think the handling, the post-processing is clear. Yeah, so far regarding the line welded stress or line welds. And let's analyze this exceeding stress in the surfaces. Let's display everything again. Maybe let's turn off the FE mesh for a second. And of course, we need the stresses in the surfaces. Yeah. So what we can see here in the table already is that we have an existing stress of more than 400 Newton per square millimeter, which is of course exceeding the limit stress. And we can also see by clicking on this table, this nice arrow, which shows us where the issue is. And the issue is where we have the bolts connecting to the connecting plates. Yeah. Now, I think it's quite clear that such a stress cannot show up in reality simply because the S235 will yield when it reaches the limit stress. Yeah, it can't get these kind of stresses. The steel will yield, it will deform, and yeah. So we get these high stresses because we use a simplified material model for our steel. The default is usually an isotropic linear elastic material model, which means we can get stresses like indefinite stresses. Yeah. Since this is not exactly correct, we could in theory use a different material model. The default material models are, however, only isotropic linear elastic models or autotropic linear elastic models. Plastic is not supported as a default setting. If you are looking for more advanced material models, you would need the nonlinear material behavior add-on. Yeah, I can select it here. And now you can see if I edit my material again, I have much more material models. For example, the isotropic plastic material model for surfaces and solids. That's the one I select. And these are the parameters for this material model. I can select the basic or bilinear or stress strain diagram. I stick to the basic diagram type. That should be enough for my case here. I could select the stress failure hypothesis. This is fine for me. And that's all I need to define. If I assign this material model to my material, it means it will yield as soon as it reaches the yield strength of about 235 Newton per square millimeter. How do we do this in the calculation? For that, I would like to show the FE mesh again. How do we consider this yielding? Well, you saw before that we had some stress peaks in that area here. The stress in those FE elements was higher than the limit stress. If that is the case, we will with the plastic material model, we will reduce the stiffness of an FE element. So we take a look at each FE element and we reduce the stiffness of those FE elements where the stress is exceeding the limit stress. If we reduce the stiffness, it means they will deform much more than the other elements where with the regular stiffness, they will take or overtake more of those forces until they maybe also reach the limit stress. Then we will reduce the stiffness again, and so on and so further. Yeah, that's the logic that we're using here. So we take a look at each FE element, and since we do it on this FE element basis, we should also check the results on FE elements. What does it mean? I can go to my calculate menu under the result smoothing function and select here constant on meshed elements. The default, I think, is this one, continuous within surface sets or otherwise within surfaces. So we get a lot of results for FE meshes, or for on each FE node we get a result, and usually we use some functionality to smooth those results, yeah, that they look nice. In this particular case, when we have this FE mesh specific look on the results, we should also smooth it constant on FE mesh elements. Yeah, so we get this pixel-like look afterwards. This setting under calculate result smoothing is for the results of RFEM 6 itself. We have the same setting in our stress strain analysis add-on. So if I go on the bottom left, stress strain analysis settings, I can also select it for this add-on, which I'm doing here. So now I can recalculate the results, and small spoiler, we won't get any stresses higher than 235 Newton per square millimeter due to this material model. So the stress check is fine. It's not a big issue anymore, but that's not the end of the check. We will get higher deformations. Yeah, we get these plastic strains probably in our structure, and that's usually what you look at when you use the plastic material model. You check the strains because the stresses are not relevant anymore. And we can run also a strain analysis inside the stress strain analysis add-on. Yeah, that's basically what the module name is. Yeah, stress strain analysis. We can activate the the strain analysis also in these global settings. Yeah, where I change the smoothing settings, I can activate here the strain analysis. I click on OK. And if I activate that analysis, I can go back into my surface configuration. And now I have this additional tab here. It shows me now strains. And again, I can select for which strain I want or which strain it should calculate. Let's say the Mises strain. And we also have a limit defined for that. We have a plastic limit strain of 5%. That's what we defined here. You can change it, of course, by simply clicking into it and defining a different value. That's what we're defining here as a limit. Of course, you could say your limit is when the strain is so big that the bolt moved completely through your connection plate, so that the structure is unstable during the calculation. I'm not sure if that's the right limit. We defined here the 5%, but at the end it's up to you. All right. That's all that I have to define here. Now I can run the stress strain analysis again. It will take a bit longer because now it's a nonlinear analysis. Yeah, each FE element is nonlinear, so we will need more iterations until we get an equilibrium, but still quite fast in that example. All right, let's have a look at the results. I get the overview table with where it says stress ratio is 1. If I check the details, it's just slightly above the limit. So for the, it's just a numerical issue, let's say, not a big deal. We can neglect this. The stresses are, of course, fine, as you can see here. We have here 235 Newton per square millimeter maximum. We also have this pixel-like display of results. That's the result smoothing that I changed. And of course, we can now also check the strains. As I said, this is now important. So instead of checking the stresses on surfaces, I can check my strains on surfaces. And this table looks also similar. We have an existing strain, 6.2 per mil. That's, however, the total strain. Yeah. The plastic strain is just 4.4 per mil. And this plastic strain will be compared to the limit of 50 per mil, which results in this plastic strain ratio. So this is the strain design, basically. This is how you can do it with the add-on stress strain analysis. And that is also what I would like to show you here. Maybe what I forgot now, we have, of course, also the strains as a result graphically, the let's say, total strain, but also the plastic strain, which is always smaller, yeah. And again, also the plastic strain ratio. Well, not much to see here, but the plastic strain. Yeah. Yes, so far regarding my 3 topics that I wanted to show today. I hope you saw something new, and I would like to see you again in a different webinar in future. So let me say bye-bye, and I hand it back to Yasmin.
I heard Yasmin has a problem with the internet connection.
All right.
And so we are ending the webinar now.
Okay, yeah. Sounds good. Then again, thank you for participating, for your questions. If there are any questions left over, then we will send you an email afterwards, of course. Yeah, have a great day. See you. Bye-bye.